Welcome back to our Calculus series. If you have been following along, you know that in Part 1, we journeyed through the rich history of calculus, tracing the independent but parallel discoveries of Sir Isaac Newton and Gottfried Wilhelm Leibniz in the 17th century. In Part 2, we built a rigorous foundation by exploring the concept of limits, which is the true backbone of all of calculus. We learned that the limit of a function f of x, as x approaches a value c, describes the behavior of f near c, not necessarily at c. Today, in Part 3, we take what may be the most important step in the entire series. We define and explore the derivative. The derivative is not just a formula or a rule to memorize. It is a profound idea about how things change. Whether you're describing the velocity of a falling object, the slope of a curve, or the rate at which a population grows, you are thinking about derivatives. Let us begin this beautiful journey together. Before we write a single symbol, let us ask the most natural question in mathematics. How fast is something changing? Imagine you're driving a car. Your odometer tells you the distance traveled, and your speedometer tells you something different. It tells you how fast that distance is changing right now, at this very instant. That is the essence of a derivative. In more formal terms, mathematics is filled with functions, relationships that assign to each input exactly one output. We write this as y equals f of x, meaning the output y depends on the input x. Now, as x changes, y changes too. But how quickly? How steeply? The derivative answers this question with extraordinary precision. It tells us the instantaneous rate of change of the function at a specific point. This idea, capturing change at a single instant, was the revolutionary insight that drove Newton and Leibniz to invent calculus. It is elegant, powerful, and we are about to make it completely rigorous. Let us start with something familiar. You know from algebra that a straight line has a constant slope. If we have the line y equals m times x plus b, the slope m measures steepness. For every 1 unit we move to the right along the x-axis, we rise m units along the y-axis. We compute this as the change in y divided by the change in x, often written as delta y over delta x, where delta is the Greek letter used to denote change in. For a straight line, this ratio is the same everywhere. But what about a curve? Consider the parabola y equals x squared. At the point where x equals 1, the curve is rising. At x equals 0, it is flat. At x equals -1, it is falling. The slope is clearly different at every point. A single number cannot describe the slope of a curve everywhere simultaneously. This is the fundamental challenge that the derivative solves. It gives us a way to assign a meaningful slope value to a curve at each individual point, even though the curve is constantly bending. Here is the key geometric idea. Suppose we have a curve defined by the function f of x, and we want to find the slope at a specific point, say where x equals a. We cannot do this directly, but we can approximate it. Pick a second point nearby on the curve, at x equals a plus h, where h is some small non-zero number. Connect these 2 points with a straight line. This line is called a secant line from the Latin secere, meaning to cut. The slope of this secant line is the change in the output divided by the change in the input. That gives us the expression f of the quantity a plus h minus f of a, all divided by h. This is called the difference quotient, and it is one of the most important expressions in all of calculus. It gives us an average rate of change over the interval from a to a plus h. The closer the second point is to the first, that is, the smaller h becomes, the better our approximation of the true instantaneous slope. This is where limits enter the picture. Now we bring in the power of limits that we studied in Part 2. As the value of h approaches 0, the second point on the curve slides closer and closer to the first point. The secant line rotates and approaches a special limiting position, a line that just touches the curve at a single point. This line is called the tangent line. The slope of this tangent line is exactly the derivative of f at the point A. We define this formally as follows. The derivative of f at the point A, written as f prime of A, is equal to the limit as h approaches 0 of the difference quotient, f of the quantity a plus h, minus f of a, all divided by h, provided this limit exists. This definition is the foundation of differential calculus. Every rule, every formula, Every technique you will ever use for differentiation traces its justification back to this single, elegant limit definition. When the limit exists, we say that f is differentiable at a. When it does not exist, f fails to have a derivative at that point. One of the first things a student of calculus encounters is that mathematicians use two different notations for the derivative, and both are used widely in textbooks, research, and applications. The first is called prime notation, introduced by Joseph Louis Lagrange in the 18th century. Here, the derivative of f of x is written as f prime of x, read aloud as f prime of x. For the second derivative, we write f double prime of x, and so on. The second is Leibniz notation, introduced by Gottfried Wilhelm Leibniz himself, and it is arguably the more powerful of the two. The derivative is written as dy over dx, read as dy dx, or the derivative of y with respect to x. This notation captures the idea of an infinitesimally small change in y, written dy, divided by an infinitesimally small change in x, written dx. Leibniz notation is especially useful in physics, engineering, and when working with the chain rule. Both notations coexist in modern mathematics, and a fluent calculus student must be comfortable reading and writing in either form. Here is an important conceptual shift. When we write f prime of a for a specific value, a, we get a single number, the slope of the tangent line at that one point. But what happens if we allow a to vary? As we move o across the domain of f prime of a produces a different value at each location. This means that f prime is itself a function. It takes an input x and returns the slope of f at that point. We call this the derivative function, and we write it as f prime of x or dy over dx. This is a profound realization. Differentiation is an operation that transforms one function into another. The original function f describes the values of a quantity. The derivative function f prime describes the rate at which those values are changing. For example, if f of x equals x squared, then f prime of x equals 2x. At x equals 3, the slope is 6. At x equals negative 2, the slope is negative 4. The derivative function encodes the slope information for the entire curve in a compact, usable form. Let us now work through the derivative of a simple function using the limit definition directly. Take f of x equals x squared. We want to find f prime of x. We start with the difference quotient, f of the quantity x plus h, minus f of x, all divided by h. Substituting, the numerator becomes the quantity x plus h, squared, minus x squared. Expanding the square, x plus h squared equals x squared plus 2xh plus h squared. So the numerator becomes x squared plus 2xh plus h squared minus x squared, which simplifies to 2xh plus h squared. Dividing by h, we get 2x plus h. Now we take the limit as h approaches 0. As h goes to 0, the term 2x plus h approaches 2x. Therefore, f prime of x equals 2x. This confirms the geometric intuition. The slope of the parabola y equals x squared at any point x is simply 2 times x. When x is positive, the parabola rises steeply. When x is 0, it is flat, and when x is negative, it falls. The derivative has captured all of this information cleanly and precisely. An important theorem in calculus connects differentiability and continuity. The theorem states, if a function f is differentiable at a point a, then f must be continuous at a. The logical implication flows in one direction. Differentiability implies continuity, but continuity does not imply differentiability. Let us understand why. If f is differentiable at a, the difference quotient has a finite limit. For this to happen, the change in f, that is, f of a plus h minus f of a, must go to 0 as h goes to 0. That is precisely the definition of continuity at a. So differentiability is a stronger condition than continuity. Now, the converse fails. Consider f of x equals the absolute value of x. This function is continuous everywhere. There are no holes, jumps, or asymptotes. But at x equals 0, the graph has a sharp corner. Coming from the left, the slope appears to be negative 1. Coming from the right, the slope is positive 1. The left-hand and right-hand limits of the difference quotient disagree, so the limit does not exist. The function is continuous at 0, but not differentiable there. Sharp corners, cusps, and vertical tangents are the classic examples of where continuity holds, but differentiability fails. Computing derivatives from the limit definition every single time would be extraordinarily tedious. Fortunately, mathematicians have derived elegant rules that make differentiation efficient and systematic. The first and most fundamental is called the power rule. It states, if f of x equals x raised to the power n, where n is any real number, then the derivative f prime of x equals n times x raised to the power n minus 1. In Leibniz notation, d over dx of x to the n equals n times x to the n minus 1. Let us verify this for a few cases. For f of x equals x squared, applying the power rule gives f prime of x equals 2 times x to the first power, which is 2x, exactly what we found from the definition. For g of x equals x cubed, g prime of x equals 3x squared. For h of x equals x to the power 1/2, which is the square root of x, h prime of x equals 1/2 times x to the power negative 1/2, which equals 1 over 2 times the square root of x. The power rule even works for negative exponents. For f of x equals 1 over x, which equals x to the power negative 1, f prime of x equals negative 1 times x to the power negative 2, or negative 1 over x squared. Two more foundational rules accompany the power rule and help us handle a wider range of functions. First, the constant rule. The derivative of any constant function is 0. If f of x equals c, where c is a fixed real number, then f prime of x equals 0. This makes perfect geometric sense. A constant function is a horizontal line. It has 0 slope everywhere. Algebraically, no matter how x changes, the output stays the same, so the rate of change is 0. The Leibniz form is d over dx of c equals 0. Second, the constant multiple rule. If you multiply a function by a constant, the derivative is that same constant multiplied by the derivative of the function. Formally, if g of x equals c times f of x, then g prime of x equals c times f prime of x. In Leibniz notation, d over dx of c times f of x equals c times d over dx of f of x. This reflects the linearity of the differentiation operator. Scaling a function scales its derivative proportionally. For example, the derivative of 7 times x cubed is 7 times 3x squared, which equals 21x squared. Together, the power rule, the constant rule, and the constant multiple rule let us differentiate any monomial term with ease. They are combinations. The sum and difference rules tell us how differentiation distributes across addition and subtraction. The sum rule states, the derivative of the sum of two functions equals the sum of their derivatives. If h of x equals f of x plus g of x, then h prime of x equals f prime of x plus g prime of x. In Leibniz form, d over dx of the quantity f of x plus g of x equals d over dx of f of x plus d over dx of g of x. The difference rule follows identically. d over dx of the quantity f of x minus g of x equals d over dx of f of x minus d over dx of g of x. These rules follow directly from the linearity of limits, which we established in Part 2. Now, combining the power rule, constant multiple rule, and sum rule, we can differentiate any polynomial. Consider p of x equals 4x cubed minus 7x squared plus 5x minus 9. The derivative is p prime of x equals 12x squared minus 14x plus 5. Each term is handled independently using the power rule and constant multiple rule, then assembled using the sum and difference rules. This is the systematic beauty of calculus. Complex problems decompose into manageable pieces. What happens when we need to differentiate the product of two functions? You might be tempted to say, the derivative of f times g equals f prime times g prime. This is incorrect, and it is one of the most common mistakes in calculus. The correct formula is the product rule. If h of x equals f of x times g of x, then h prime of x equals f prime of x times g of x plus f of x times g prime of x. In Leibniz notation, d over dx of f times g equals df over dx times g plus f times dg over dx. A helpful mnemonic is derivative of the first times the second plus the first times the derivative of the second. To understand why this works, recall the difference quotient definition. When both f and g are changing simultaneously, there is a cross term that survives in the limit. It is not simply the product of the two individual changes. Let us apply this. Suppose h of x equals x squared times the sine of x. Then h prime of x equals 2x times sine of x plus x squared times the cosine of x. The product rule becomes especially powerful when chained with other rules, and it is the gateway to differentiating increasingly complex functions built from simpler components. Just as the product rule handles multiplication, the quotient rule handles division. If h of x equals f of x divided by g of x, and g of x is not equal to 0, then the derivative is given by h prime of x equals the quantity g of x times f prime of x minus f of x times g prime of x, all divided by the square of g of x. Written compactly, h prime of x equals the quantity g times f prime minus f times g prime, all over g squared. A useful mnemonic for remembering the order in the numerator. Low d high minus high d low over low squared, where high is the numerator function f, low is the denominator function g, and d stands for derivative. Let us work an example. Suppose h of x equals sine of x divided by x. Then f of x equals sine of x, with f prime of x equals cosine of x. And g of x equals x, with g prime of x equals 1. Applying the quotient rule, h prime of x equals x times cosine of x minus sine of x times 1, all divided by x squared, which simplifies to x cosine of x minus sine of x over x squared. This function appears frequently in signal processing and physics, where it is called sense of x. If the power rule, product rule, and quotient rule are essential tools, the chain rule is the crown jewel of differentiation. It handles composite functions, functions of functions, and it is indispensable in virtually every area of applied mathematics. If we have a composite function h of x equals f of g of x, the chain rule states h prime of x equals f prime of g of x times g prime of x. In Leibniz notation, if y is a function of u and u is a function of x, then dy over dx equals dy over du times du over dx. This multiplicative structure is one reason Leibniz notation is so powerful. The derivative fractions appear to cancel like ordinary fractions, which gives strong intuition even when the formalism is subtle. Consider h of x equals the sine of x squared. Here, the outer function is sine of u, and the inner function is u equals x squared. Differentiating the outer function gives cosine of u, evaluated at the inner function, giving cosine of x squared. Multiplying by the derivative of the inner function, which is 2x, we get h prime of x equals 2x times the cosine of x squared. The chain rule is the key to unlocking derivatives of exponentials, logarithms, trigonometric compositions, and virtually every function encountered in science and engineering. Trigonometric functions are ubiquitous in mathematics, and their derivatives have elegant, cyclical patterns worth knowing deeply. The derivative of sine of x is cosine of x, written d over dx of sine of x equals cosine of x. The derivative of cosine of x is negative sine of x. D over dx of cosine of x equals negative sine of x. Notice the cycle. Differentiating sine gives cosine. Differentiating cosine gives negative sine. Differentiating negative sine gives negative cosine. And differentiating negative cosine gives sine again. A four-step cycle. These results follow from the limit definition and require the two fundamental trigonometric limits. The limit as h approaches 0 of sine of h over h equals 1, and the limit as h approaches 0 of the quantity cosine of h minus 1 over h equals 0. From sine and cosine, the derivatives of the other four trigonometric functions follow by the quotient rule. The derivative of tangent of x is the secant squared of x. The derivative of secant of x is secant of x times tangent of x. The derivative of cosecant of x is negative cosecant of x times cotangent of x. The derivative of cotangent of x is negative cosecant squared of x. When combined with a chain rule, these 6 formulas allow us to differentiate extraordinarily complex trigonometry. Among all mathematical functions, the natural exponential function, written e to the x, where e is Euler's number, approximately 2.71828, holds a truly unique position. It is the only function, up to constant multiples, that is its own derivative. Formally, d over dx of e to the x equals e to the x. Let us appreciate why this is remarkable. The function e to the x describes a curve that rises steeply as x grows. At any point on this curve, the slope equals the function's value at that point. If the curve reaches a height of 10, the slope is 10. If it reaches a height of 1,000, the slope is 1,000. Growth begets faster growth, and this self-referential property is precisely why exponential functions model phenomena like population growth, radioactive decay, and compound interest. More generally, the derivative of e to the power u of x, where u is a function of x, follows from the chain rule. It equals e to the u of x times u prime of x. And for the general exponential base a to the x, where a is any positive real number not equal to 1, the derivative is a to the x times the natural logarithm of a. These results make the exponential family among the most tractable in all of analysis. The natural logarithm, written as the natural log of x, or ln of x, is the inverse function of the natural exponential. Its derivative is one of the most important in calculus. D over dx of the natural log of x equals 1 over x, for x greater than 0. This result can be derived from the definition of the inverse and implicit differentiation, which we will discuss in a later scene. Let us think about what this says geometrically. For large values of x, the function ln of x grows very slowly. The slope 1 over x becomes very small. For small values of x near 0, the slope 1 over x becomes very large, reflecting how steeply the logarithm rises near the origin. To differentiate a general logarithm with base a, written log base of x, we use the change of base formula from algebra. Log base a of x equals the natural log of x divided by the natural log of a. Differentiating, d over dx of log base a of x equals 1 over the quantity x times the natural log of a. When combined with the chain rule, the derivative of the natural log of u of x is u prime of x divided by u of x. This form appears constantly in optimization, probability theory, and information theory, where logarithms are the natural language. So far, we have differentiated functions where y is expressed explicitly in terms of x, that is, y equals some expression in x. But many important curves cannot be written this way. Consider the equation of the unit circle x squared plus y squared equals 1. Here, y is not a function of x in the global sense. The circle fails the vertical line test. Yet we can still speak of the slope of the circle at specific points, and we can find it using a technique called implicit differentiation. The idea is to differentiate both sides of the equation with respect to x, treating y as an implicit function of x, and applying the chain rule wherever y appears. Differentiating x squared plus y squared equals 1 with respect to x. The derivative of x squared is 2x. The derivative of y squared requires the chain rule. It is 2y times dy over dx, since y is a function of x. The derivative of the constant one is 0. So, 2x plus 2y times dy over dx equals 0. Solving for dy over dx, we subtract 2x from both sides and divide by 2y, giving dy over dx equals negative x over y. This tells us the slope of the unit circle at any point x, y on the circle. Implicit differentiation opens up a vast world of curves and relationships that cannot be handled by explicit formulas alone. The derivative of a function is itself a function, and if that derivative function is differentiable, we can differentiate it again. The result is called the second derivative. We write this as f double prime of x in prime notation, or d squared y over dx squared in Leibniz notation, where d squared y over dx squared is read as d squared y dx squared. This notation, though it looks like a fraction, represents iterated differentiation, not a ratio of squares. We can continue. Differentiating a third time gives the third derivative, written f triple prime of x or d cubed y over dx cubed. For orders higher than 3, we typically write f to the power n in parentheses of x, or d to the n y over dx to the n. What do higher derivatives mean? The first derivative f prime of x gives the rate of change of f, its instantaneous velocity, if you will. The second derivative f double prime of x gives the rate of change of the rate of change, that is, acceleration. In the context of a position function s of t, the first derivative is velocity v of t, the second derivative is acceleration of t, and the third derivative is called jerk, the rate of change of acceleration. Higher derivatives also encode curvature, which tells us how rapidly a curve bends in space. The second derivative provides crucial geometric information about a function's graph, specifically about its concavity. Concavity describes which way a curve bends. If the second derivative f double prime of x is positive on an interval, the first derivative f prime is increasing on that interval, meaning the slope is getting steeper as we move right. Geometrically, the curve is bending upward, like the inside of a bowl. We say the function is concave up on that interval. Conversely, if f double prime of x is negative on an interval, the first derivative is decreasing, the slope is becoming less steep or more negative as we move right. The curve bends downward, like the outside of a hill. We say the function is concave down. Points where the concavity changes, where the second derivative changes sign, are called inflection points. These are the points where the curve transitions from bending upward to bending downward, or vice versa. The second derivative test also helps identify the nature of critical points. If f prime of c equals 0 and f double prime of c is greater than 0, then f has a local minimum at x equals c. If f double prime of c is less than 0, then f has a local maximum at c. The first and second derivatives together give us a complete geometric portrait of a function. Derivatives is finding the maximum and minimum values of functions, a process called optimization. A critical point of a function f is any value c in the domain where either f prime of c equals 0 or f prime of c does not exist. These are the candidates for local maxima and minima, called local extrema.
Why?
Because at a local maximum or minimum, the function must momentarily stop increasing or decreasing. The tangent line is horizontal, slope 0, or the function has a corner or cusp where no tangent exists. The first derivative test helps us classify critical points. Suppose C is a critical point. Examine the sign of f prime on either side of C. If f prime changes from positive to negative at C, meaning f was increasing then decreasing, then f has a local maximum at C. If f prime changes from negative to positive, f was decreasing then increasing, then f has a local minimum at C. If the sign of f prime does not change, the critical point is neither a maximum nor a minimum. It may be an inflection point. The extreme value theorem guarantees that a continuous function on a closed-bounded interval always attains its global maximum and minimum, and they must occur either at critical points in the interior or at the endpoints of the interval. The mean value theorem is one of the most important and far-reaching theorems in differential calculus. It connects the average rate of change of a function over an interval to the instantaneous rate of change at some interior point. The theorem states, if f is continuous on the closed interval from a to b and differentiable on the open interval from a to b, then there exists at least one point c strictly between a and b such that f prime of c equals the quantity f of b minus f of a divided by b minus a. In other words, the slope of the tangent line at some interior point C equals the slope of the secant line connecting the endpoints a, f of A and b, f of B. The geometric interpretation is vivid. If you connect 2 points on a smooth curve with a straight line, there must be at least one point along the curve where the tangent is parallel to that secant line. This is intuitively obvious, but requires proof. The mean value theorem has profound implications. It implies that if f prime of x equals 0 everywhere on an interval, then f is constant on that interval. It also implies that if two functions have equal derivatives everywhere, they differ by a constant, a fact used constantly in integral calculus when computing antiderivatives. Recall from Part 2 that limits can be challenging when they produce indeterminate forms, expressions like 0 over 0 or infinity over infinity, where the value cannot be determined by simple substitution. L'Hopital's rule, named after the French mathematician Guillaume de L'Hopital, provides an elegant way to evaluate such limits using derivatives. The rule states, suppose f and g are differentiable near a point A, g prime of x is non-zero near A, and the limit of f of x over g of x as x approaches A produces an indeterminate form of 0 over 0 or infinity over infinity. Then, the limit of f of x over g of x as x approaches A equals the limit of f prime of x over g prime of x as x approaches A, provided this second limit exists or is infinite. In plain terms, replace the numerator and denominator by their respective derivatives and try the limit again. For example, the limit as x approaches 0 of sine of x over x is the indeterminate form 0 over 0. Applying L'Hopital's rule, differentiate the numerator to get cosine of x and differentiate the denominator to get 1. The new limit is cosine of 0 over 1, which equals 1. This confirms the fundamental trigonometric limit from Part 2. L'Hopital's rule can also handle other indeterminate forms, such as 0 times infinity or 1 to the power of infinity, after appropriate algebraic manipulation. Related rates problems are among the most vivid and practical applications of the chain rule and implicit differentiation. The setting is always the same. Two or more quantities are related by some equation, and both are changing with respect to time. We know the rate of change of one quantity and want to find the rate of change of the other. The strategy is to differentiate the relating equation with respect to time t, applying the chain rule to every variable since all variables are implicitly functions of t. Consider a classic example. A spherical balloon is being inflated. Its volume v is related to its radius, r, by the formula v equals 4/3 times pi times r cubed. Differentiating both sides with respect to t, dv over dt equals 4 pi r squared times d r over dt. Here, dv over dt is the rate at which the volume is increasing. Perhaps we know it is 10 cubic centimeters per second. Given that rate and the current radius, we can solve for dr over dt, the rate at which the radius is growing. Related rates problems appear throughout physics, engineering, biology, and economics. The ladder sliding down a wall, the shadow lengthening as a person walks, the water draining from a conical tank, all are governed by related rates reasoning. Each problem demands translating a physical situation into mathematical relationships and then differentiating carefully. Consequences of the derivative is linear approximation, the idea that near any point where f is differentiable, the function looks approximately like a straight line. Formally, if f is differentiable at the point A, then for values of x close to A, we have the approximation. F of x is approximately equal to f of a plus f prime of a times the quantity x minus A. The right side is the equation of the tangent line to f at x equals A, and it is called the linearization of f at A, often denoted L of x. This is profound. Near the point of tangency, the tangent line is a local stand-in for the curve. The error between the true value f of x and the linear approximation L of x becomes negligible as x approaches A. Leibniz formalized this idea through the concept of differentials. If y equals f of x, the differential dx represents an infinitesimally small change in x, and the differential dy is defined as f prime of x times dx, the corresponding change in y as predicted by the tangent line. Linear approximation is the foundation of numerical methods, engineering tolerances, and the propagation of error in measurements. It explains why so many functions are approximated as linear in small neighborhoods, a cornerstone assumption in physics and applied mathematics. The language of derivatives is the native language of physics. Suppose the position of a particle moving along a straight line is described by a function s of t, where s is measured in meters and t is measured in seconds. The first derivative of position with respect to time is velocity. V of t equals ds over dt. Velocity tells us how fast the position is changing and in which direction. Positive velocity means moving in the positive direction. Negative velocity means moving in the negative direction. The second derivative of position, equivalently, the first derivative of velocity, is acceleration of t equals dv over dt equals d squared s over dt squared. Acceleration tells us how fast the velocity is changing. For example, if s of t equals 5t squared minus 3t plus 2, then v of t equals 10t minus 3, and a of t equals 10. The acceleration is constant, which corresponds to uniform acceleration, like a ball in free fall near Earth's surface, where gravitational acceleration is approximately 9.8 meters per second squared. This connection between derivatives and physical motion is not coincidental. It was Newton's motivation for developing calculus in the first place. Every law in classical mechanics is expressed as a differential equation, a relationship between a function and its derivatives. Optimization is the art and science of finding the best solution, the maximum profit, the minimum cost, the fastest path, the strongest structure. Derivatives are the central mathematical tool for solving optimization problems. The procedure follows a well-defined sequence. First, identify the quantity to be optimized and express it as a function of one or more variables. Second, use any given constraints to reduce the function to a single variable. Third, find the critical points by setting the derivative equal to 0 and solving. Fourth, use the first or second derivative test to determine whether each critical point is a maximum, a minimum, or neither. Fifth, check the boundary values if the domain is a closed interval, since extrema can occur at endpoints. A classic example is the fenced enclosure problem. Given a fixed length of fencing, what dimensions of a rectangular plot maximize the enclosed area? If the total fencing is P, and the rectangle has length L and width W, the perimeter constraint gives 2L plus 2W equals P, expressing area A equals L times W in terms of one variable, and differentiating gives dA over dW equals P over 2 minus 2W, set equal to 0, yielding W equals P over 4. By symmetry, L equals W. The optimal rectangle is a square. Optimization problems appear in economics, engineering, biology, and architecture, and they're solved by the same logical deployment of derivatives. Derivatives are not only tools for theoretical mathematics, they are the engine behind powerful computational algorithms. One of the most famous is Newton's method, also called the Newton-Raphson method, for finding roots of equations. Suppose we want to solve f of x equals 0 for some differentiable function f, but no closed-form solution is available. We begin with an initial guess x sub 0 near the true root. The tangent line to f at x sub 0 has equation y minus f of x sub 0 equals f prime of x sub 0 times the quantity x minus x sub 0. Setting y equals 0 and solving for x gives the next approximation x sub 1 equals x sub 0 minus f of x sub 0 divided by f prime of x sub 0. We then repeat x sub n plus 1 equals x sub n minus f of x sub n divided by f prime of x sub n. Under favorable conditions, this sequence converges extremely rapidly to a root. Typically, each step doubles the number of correct decimal digits, a behavior called quadratic convergence. For example, to solve x squared minus 2 equals 0, that is, to find the square root of 2, starting from x sub 0 equals 1, Newton's method produces the sequence 1, 1.5, 1.4167, 1.41421, converging to the true value approximately 1.4142136. Newton's method is the foundation of many modern numerical solvers used in computing, finance, and scientific simulation. We close this chapter with a preview of what awaits in Part 4, and with perhaps the most beautiful result in all of calculus, the fundamental theorem of calculus. Throughout this video, we have studied the derivative, a machine for measuring instantaneous change. In Part 4, we will study the integral, a machine for measuring accumulation. These two concepts might appear to be completely separate ideas. The derivative asks, how fast is this changing right now? The integral asks, how much has accumulated over this interval? And yet, The fundamental theorem reveals that differentiation and integration are inverse operations of each other, bound together in a profound and surprising unity. The journey continues in Part 4.